My name is Connor, and this is Nathan, and we're here to discuss our project in which we modeled Bitcoin load spikes as far as the network in terms of transaction rates. So take it away.
Okay, so our goal for this project, our rationale, what we're interested in is black swan events where many transactions arrive in a short period of time. So this could be because of DOS attacks, so just a few entities creating many transactions, or there could be events where many different people want to make a transaction, and it could be benign, like a shopping spree. So we wanted to answer two questions. How does a temporary spike in transaction rate affect confirmation delay distribution? And for a given spike shape, if we could magically change the block size, how would that affect the evolution of the system?
So our simulation was mainly based off of the Bitcoin traffic bulletin, number 34. Appreciate it. So I don't know if you guys are familiar with this post, but in that simulation, the author models both transaction rates and block mining rates in a Poisson distribution, and then calculates the expected time for a transaction to be confirmed. So we took the same sort of style and then made a couple changes to the actual model. Our mempool is modeled as an infinite FIFO queue, so transactions are continuously appended to this queue and then processed in each block. We used a constant transaction size of 250 bytes, and the main ways in which our model differs from the Bitcoin traffic bulletin is that our block size is variable, so we can actually adjust the rate or the size of the block for a given simulation, as well as define spike profiles, in which, as you see on the right, we have this time-varying spike, and so we can actually model that into the simulation so that we have different loads at different points in the simulation, so we can log the confirmation times for each one of those spikes and see the comparison.
One other thing about this slide is that probably Poisson distribution for block arrival rate makes sense because hopefully the chance of finding two different blocks is completely independent. Transaction arrival rate as a Poisson distribution is like a simple way to approach it, but our whole premise is that transactions sometimes violate the assumptions of Poisson distribution, which is independence of events within a time period. So we're accounting for that by varying the Poisson distribution's rate in that step function.
All right, so this is an example of the Bitcoin traffic bulletin's results. So here we have an S-curve essentially displaying the cumulative probability distribution of a transaction's confirmation time given the load on the network. So on the right-hand side, you see a legend that goes from 0.1% to 100% of the Bitcoin loads network. And you see going across the graph that those transaction times tend to increase, and the separation increases with the increase in load. So for example, the far most left curve terminates at about 380-ish seconds, so just over 5-6 minutes.
Which is a really low transaction rate.
Which is what you'd expect from a essentially empty network. Versus all the way on the right, the purple plot is about 10,000 seconds per transaction. So you can see like the huge increase just based on the load of the network.
So on the right, 100% transaction rate means in this model 3.5 transactions per second, which is just proportional to the block size and how large transactions are. And another thing to point out is the time scale on the x-axis is logarithmic. So even though the S-curves all look to have the same shape, the tails are a lot worse as the load gets high. So it could be, I don't know the exact here, like it could be the case that like 20% of transactions have to wait over 3 hours or something like that once the load is high enough. So this is the result from Bitcoin traffic bulletin that we're trying to extend. So we don't have results that we felt comfortable sharing because we think we have bugs. So sadly, we just have this sketch of what you could imagine. And then hopefully, yeah, you could tell us if you would like to see these results and you think they would be useful. So kind of a sketch of what we wanted to do is have a time series plot showing the rate jump up in the square wave. And then we expect that if we plotted the mempool size over time and smoothed that, it would look like what you see here. So the memory pool starts growing, assuming the high rate is higher than the capacity of the network. And then we expect the memory pool would drain over time after the spike ends, if that were to occur in a fictional universe. So we would be interested in like how long is that hump? So how long does it take the memory pool to drain? And we would be interested to, at each of these arrows, create another distribution plot like the one from the original model and see what's different.
And I think one thing to note on that is that the original simulation, you fixed a block size and fixed the transaction rate. And because we're actually varying the transaction rate, we can model spikes that are, say, tens or thousands of times the normal Bitcoin like network transaction rate, and then see the network's response to that, as opposed to just being able to fix a constant rate that's above 1 or above 100% of the network capacity, because then you just have an infinite growing queue. So we're able to see those network responses in our simulation. Thank you.
So, right, and then the next step is imagine a different block size and see how that changes the length of this curve. So this is we need to do further work, obviously, but one thing we need to do is more background work, because this seems like a fairly simple problem or model that would probably exist elsewhere in the history of like router design or evolution. And we're not that familiar with queuing theory, so this is sort of like our weekend project to discover for ourselves. And also, I wouldn't be at all surprised if there's other work specific to Bitcoin that we're just not aware of, because there's many fire hoses on the net of information about Bitcoin.
And then as far as future work and how we plan to improve our model, so given that the general philosophy or the outcome of the simulation may be similar to events in queuing theory, we want to expand our model so that it's more powerful and able to handle certain cases and get like more accurate simulations for the Bitcoin network itself. One thing we'd like to do is compare against empirical data, so look back through previous transaction rates, just to compare how our load spike simulation fits real imperative data that we see in history. And the second way is that we want to expand our simulation to include things like transaction loss when the user resubmits transaction, as well as replaced by fees. So, and that is reordering transactions in the queue, because like I said earlier, our model is currently a FIFO queue, so no transactions are lost, and fees do not take into account in our simulation. So, yep. Expanding on those, I think, would help give us a more accurate model of the actual load spike simulation for Bitcoin. Thank you.
So yeah, I just wanted to say one last bit about exploring queue reordering and things like that is my personal interest with this project, because I think there's been a lot of discussion about, there's been discussion about both of these topics, but some people are focused on, for the standard operation of the network, how much load can it handle. But there's also the exceptional case of denial of service attack or shopping sprees. And I'm particularly interested in learning more about the mechanics between user behavior and miners, so the connection between wallets and miners or full nodes. So yeah, that's it for us.
All right. Thanks, guys.
Thank you, Nathan and Connor.